Our second tutorial is given by Professor Giulia Semeghini, who's actually been here 2 years? Well,
one and a half. Yeah. No, it's okay. You don't count the postdoc.
And so she's a new faculty member in physics, but she's also, of course, as I mentioned earlier, an important cog in the new evolving Harvard Quantum Initiative, which is our budding young quantum engineering department. Mm-hmm. And she's going to talk to you today about kind of the next step in this is, exploring quantum computing, specifically implementations, applications, and future prospects.
Thank you, Bill. Okay, very good to see you all here. I've been tasked to give this second tutorial, and what I'll try to do is to take what Nishan just explained to you about qubits and gates and try to answer the question that was just asked, like how did people take up this challenge and try to do this in a real system? And I will spend most of the talk on that. Then in these coming days, you will hear talks about all these different systems, but I think it's nice to get sort of an overview and see the difference between these different implementations. I will mention towards the end a few examples of applications that I think will give you a feeling of where the field is right now. And then I will conclude with some questions about what are the challenges that we have ahead of us and what are the next steps that we would like to achieve. So to begin, I think Nishan had a very similar slide, but we hear a lot about quantum computers these days. These are just some examples of newspaper articles that you might have read or seen in the past few years. And you certainly see a lot of excitement. You see very confusing things. This is something I found a couple of years ago. There are people that promise to sell you a desktop quantum computer for only $5,000. I didn't go too much into the details. I don't really know what you will get if you pay those $5,000. But also at the same time, there are pretty prominent scientists who say that quantum computing has a hype problem, too much hype. And what is actually happening is not as exciting as the hype would promise you. So what Bill asked me was to give you sort of an overview of where the field actually is. So this is what I'll try to do. I don't think I will fully answer these questions, but at least I will give you some idea. And so what is actually happening is what I'll try to tell you a little bit about. So to begin this, I would like to start from the beginning. So what was the original intuition behind the idea of quantum computers? So this original intuition, we can date it back to Richard Feynman, who in the 80s wrote this. So I'll look at this quote from him where he says, we can, in principle, think of making a computing device in which the numbers are represented by a row of atoms, with each atom in either of the two states. So you take a quantum particle. This quantum particle has these discrete energy levels. You identify two of them as your bit states. Those are zeros and ones, and that's your input. Then you have the Hamiltonian start. So you have some Hamiltonian that determines the time evolution of your system. The ones move around, the zeros move around, and finally, a particular bunch of atoms represents the answer. Nothing could be made smaller, nothing could be more elegant. So this was kind of his intuition. What he was thinking in those years was, we're trying to simulate quantum systems, quantum phenomena using classical computer, and that is very inefficient. What if we were able to simulate this quantum phenomena using actual quantum systems that have all those strange properties of quantum systems inherent to them? And to start the talk on a positive note, I just would like to show you that what Feynman talks about in this paragraph is basically now a reality in labs. So these are pictures from my postdoc lab here at Harvard. And what you see here is an array of atoms. So each green dot that you see here is a single neutral atoms. And in these atoms, we're encoding zeros and ones, and we're having them move around, evolve according to their Hamiltonian. And then we're reading out some of them to determine what is the state of the system, and so what is the solution to a certain algorithm that we've been implementing during this sequence that you see here. So this is to start with some positive news. What was at the basis of the original intuition for quantum computers is actually happening to some degree in our labs. But then let's be real, does that mean that this is done? That we've done the whole thing? Of course not, otherwise we wouldn't be here talking about it. So what I'll try to do now is to look at what has been realized so far and what are the challenges ahead. So before going into that, let's briefly remind ourselves what are the problems that we hope quantum computers could help us with. So a quantum computer doesn't promise to solve everything in your life, but only certain aspects of real-world problems that we hope to solve using this type of systems. So there are two main classes of problems that we would like to tackle. The first one are difficult problems that are now solved using classical machines, but with methods that are both expensive and inefficient, and also they're brute force methods that sometimes lead to suboptimal solutions. So you don't find the actual solution, you find some approximation to the solution that could be quite good or not that good depending on the specific case. And then there is a second class, which are actually the impossible problems, meaning those that you really cannot even try to solve using a classical machine. So these are the two classes that we would like to use quantum computers for. And among these, there are different types of problems. The first type of problem is what we can call a quantum simulation, so quite similar to Feynman's original idea. There are some quantum phenomena that are very complex, and they're hard to study on classical machines. And two examples are, for example, understanding and designing quantum materials. These have very complex interactions. They have a lot of degrees of freedom, and so they're hard to simulate with classical methods. So could we use quantum computers to do this? And as I will show you later, we're actually already doing this. And you can immediately see that this has very serious technological applications, because being able to design new quantum materials could really benefit a lot of different applications. But also another example of quantum simulation would be the study of chemical structures and processes. Again, there are complex molecules or complex chemical processes and reactions that you would like to study with these methods. And you can immediately think, for example, that one application of this would be in medicine and in the development of drugs. Then there are other types of problems. For example, the optimization problems, for example, for networks or complex systems. There are problems of factoring of large numbers, number theory, encryption. And then there's more with quantum sampling, and even trying to find ways to accelerate artificial intelligence methods. These are some of the examples that people have thought of, but of course there could be more, Our creativity is the only limit to this list. So in what I explained here, there are two different paradigms for this quantum machine. One is an actual universal quantum computer that I think is what people mainly think about, meaning a quantum computer that can really do it all. So any of these things could be solved on that universal quantum computer, in the same way as you can use your classical computer now for everything that you would like to do. But there is another paradigm that is closer to what we have in our labs right now, which is a programmable quantum simulator, meaning, let's say you have a specific material that you would like to simulate, you have a quantum system in your lab that is controllable, and that you can program such that you can recreate exactly that phenomenon that you would like to study. And these systems have some programmability. You can tune a few parameters to study different types of problems, but they're not universal, meaning you cannot do all of these different things using this programmable quantum simulator. What I'll show you today is what is the progress on platforms that, in a sense, aim to do both. Some are more focused on this ultimate goal, some have done both. And I'll show you a little bit about how close are we to these goals. Okay. So what I will start with is an explanation of the platforms. And as you heard from Nishant, what we would like to do is to, first of all, find ways to encode qubits, so to store information in some quantum system, and also to perform gates, so to have logical operations between these qubits. And now we will talk about what people, try to do to actually do this in real life. And there are different platforms that have been developed in the past, few decades, I would say. And here are some examples. People have used ions, atoms, superconducting qubits, spins, defects in solids, photons, etc. And so here you see some pictures from these different experiments. And the goals that people are trying to achieve within these experimental platforms are mainly two. And they represent what I call here the ultimate quantum rivalry, because these two goals kind of fight against each other, as I will tell you in a second. So the first goal is to be able to control these qubits so to encode this information in a reliable way, but also to do operations on these qubits with high fidelities. And this has been done, is being done with a few qubits quite well in different platforms, as I will show you. But then the second goal is you would like to scale the system size to large enough numbers, because the information that you can encode in your computer scales exponentially with the number of qubits, but you need enough qubits to have enough information that you can put on your computer. The thing is, as you probably know, if you have a quantum system, the more you make it interact with other degrees of freedom and with the environment, the higher the chances of it collapsing. And so while we're typically pretty good at doing this first thing with a few qubits, as soon as you start scaling, things get complicated. And so what we're trying to do in many labs all over the world, in universities, but also in quantum industry, is to achieve these two goals together. Okay, so what is the status right now? I would say, so here I sort of anticipate some of the things that we will see. I think this is an era of quantum discovery, meaning we're already at a stage where we have these experimental platforms in our labs that are already able to do things that are beyond what classical supercomputers can do. And so I will show you a few things that experiments on quantum platforms have discovered or have been able to study that are not possible on classical computers. We've been testing quantum algorithms for these quantum computers and exploring new scientific applications. But in the meantime, we're trying to build bigger and better quantum machines, because of course, the two things need to go together, right? We're testing the smaller machines we have right now, but in the meantime, we're also trying to make them better and bigger. Okay, so let's start with an introduction of these different quantum platforms. Also, by the way, if you have questions at any time, please raise your hand and ask them also during the talk. So there are two different approaches that people have used to develop quantum platforms. One is to just use quantum particles that nature gives you. And so people have used atoms, ions, photons. And so what you're trying to do here is to identify natural systems where you can isolate a qubit, so a two-level system. And not only you can identify the qubit, but you can control it, and you also can make different qubits interact with each other. So you can create entanglement, as you've heard before. The other approach is to use engineered quantum devices, so something that is man-made, that is fabricated in a lab. And a few examples in this category are superconducting qubits, spin qubits in quantum dots, and defect centers. And here, basically, what you're trying to do is to fabricate artificial atoms. So objects that have very similar behaviors to these natural quantum particles. For example, they have discrete energy levels such that you can isolate the two-level system. You can control them with some external field, for example, and so on. And so these are kind of the two approaches that I will show you, and I will show you a few examples for each of these. Okay, so we will start with the engineered quantum devices, because I think when you think of a quantum computer, you probably think of something like this. If you go on your computer and search quantum computers, you will find, the first result that Google gives you is this, because this is their thing. But so these are superconducting qubits. Actually, this is just a fridge. This gold shiny thing is basically just a fridge that brings your system down to very low temperatures. The superconducting qubits are somewhere here in a tiny, tiny region of this big picture. But what are these superconducting qubits? So the idea is to create a small circuit And in particular, we will start looking at an LC oscillator. So you have an inductor L and a capacitor C in your little circuit. And if you write down the energy of this circuit, you'll find something like this. So you have the energy stored in the capacitor is proportional to the square of the charge that is accumulated on the plates. And then you have the energy stored in the inductor, which is proportional to the magnetic flux on the inductor squared again. Now, if you look at this and you've studied quantum mechanics, maybe you think, oh, this looks like a harmonic oscillator. Maybe not, but I'll tell you. What you can do is to rewrite this as a harmonic oscillator Hamiltonian, where you map the momentum degree of freedom on the charge and the position degree of freedom on the flux phi. And so by shuffling around some constants, you can write this energy here as this Hamiltonian on the right side. And this should really remind you of the harmonic oscillator Hamiltonian. And being in the same form as the harmonic oscillator means that you have quantized energy levels. So you have that your energy levels correspond to the modes of the quantum oscillator, and they are all equally spaced by some frequency omega c. So this is nice. You have your discrete energy levels, and so you could think, oh, see, I have an artificial atoms. I can identify my two energy levels and use this as a qubit. The tricky thing here is that being all the energy levels equally spaced, it's really hard to isolate only two of those states, because let's say that we're trying to excite the state from the 0 energy state to 1. That resonant frequency is the same as this second resonant frequency. And so it's hard to only keep your system in those two levels. So a very clever idea that people had was we would like to have this spacing be uneven. And to do that, we can introduce some nonlinearity. And to do that, we substitute the inductor on this circuit here with a Josephson junction. So this is a very quantum thing. If you have never seen a Josephson junction, don't worry. It doesn't matter. I hope at some point you do, because it's a very cool thing. And it's a very cool demonstration of quantum physics. But basically what a Josephson junction is just this little device where you have two superconducting pieces that are connected by an insulating layer in between. I'm not going to go in any details of how these work. Just to remind you, a superconductor is a material where you can have dissipationless current flow when you cool it down below a certain critical temperature, which is why we need this shiny, very nice fridge up here. So what happens when you substitute your inductor with this thing is that you have an inductance that is nonlinear as a function of some parameter that is related to these superconducting materials. So again, no details, but this changes the Hamiltonian in a way that makes the separation between this energy level, as I said, uneven. So the energy difference between the first and the ground state and the first excited state is different from the difference between the next two levels, which means that now I can finally isolate my two levels, and so I can get myself an actual qubit. And this is what is called a transmon qubit in superconducting systems. So now we have a qubit. We can use these the first two levels of this ladder here. Then the next thing we want to do is to be able to do control on the single qubit and also to do readout. And so again, here I won't give you too much details, but what you do is you add a few elements to your circuits such that you can drive the system. And so for example, here you have this control line where you can send microwave photons to drive transitions between the two qubit states. That energy difference here is a few gigahertz, so that corresponds to microwave photons. And then you have another control line for readout and so on. Okay, so what you can imagine here is just a little chip. It's a superconducting circuit, so all the elements, most of the elements are superconducting, not all of them. And then finally, what we want to do is to create entanglement, right? So here I'm just showing you one qubit, but then if you put two qubits next to each other and you add some coupling between them, and you can do this in different ways. You can have a coupler in between, or you can have just inductive coupling between the two. Then you can let the system evolve under its interaction Hamiltonian and then produce entangling gates. Okay, so this should give you a little bit of a flavor of how superconducting qubits work. Now let's switch to the second quantum device that I want to show you, which are quantum dots. So this is, kind of a typical image of quantum dots that you can find, again, online. And what is the key idea here? The idea, so before you had that the quantum states, the qubit was encoded basically in the current on this little circuit, right? In this case, what we want to do is to isolate single charges, typically electrons, sometimes holes, in a solid system. And so the qubit is going to be encoded in the electron. But here the question is, how do I isolate an electron so that I can control it individually? And this is where the quantum dot comes in. So what people have done is to create these quantum dots that are basically small regions in a solid state system where you can confine electrons, both by using the material that you use and also by using electrostatic potentials. So what happens here is you have two layers of two semiconductors that have different band gaps. And if you do this thing, again, no details here, you can create a layer in between the two where you localize electrons. So you have this, what is called a 2D electron gas. So you have this layer where the electrons are confined along one direction and they can move on a 2D plane. But then you also add these electrostatic potentials that are created by these metal gate electrodes. So those gates produce a repulsive potential for the electrons, such that the electrons are confined only to the blue regions of this sketch here. And so this thing here is a little quantum dot. It's a little box where the electrons can sit, but it's surrounded by barriers, okay? So you have that box, but to get into that box, you need to tunnel through a barrier. So the quantum dot is also what you see. So this is an actual picture of your solid state system here, and these circles correspond to where the quantum dots are. So when you do this, you create a 3D confinement for the electrons, and so the Hamiltonian that you have is basically the same for a particle in a box. So you have confinement in 3 directions. And so this means that, again, you have discrete energy levels. And what you can do is to tune your system such that you can have only one electron in each of these quantum dots. And I will show in a second how that works. But all these different properties make this system an artificial atom. Again, you have these discrete energy levels. You can control your system in between these energy levels and so on. So how does this work? So this is what I'm showing here is the electrochemical potential for the quantum dot. You can think of these as energy levels. It's not exactly, but kind of. So you have these standing barriers that sort of isolate your quantum dot. So the quantum dot is inside, and outside you have these reservoirs. So these blue regions here, you have other electrons there that can tunnel into your quantum dot. But basically what you can do, so again, you have these discrete energy levels. This corresponds to having 1 electron inside. This corresponds to having 2, and so on. And what you can do is to tune using electric fields in your system. You can tune the electrochemical potential of the reservoir with respect to the electrochemical potential inside the quantum dot. And so you can choose, do you want 3 electrons? Do you want 2? Do you want 1? By tuning these, you can decide how many are allowed to tunnel in. Okay, so in this situation that I plotted here, you can only have 1. Now, the next thing you can do is you can apply a large magnetic field such that the spin up and spin down states of the electron are splitted in energy because of the Zeeman effect. And so you find yourself in this situation where you have only 1 electron that can sit in the quantum dot, and it can be in the up or the down spin state, which are separated in energy. And this, you can see now, is a very nice qubit, right? Where the qubit state is encoded in the spin degree of freedom of the electron. Okay, so then the next thing you would like to do, again, is to be able to control and read out this qubit. And to do this, you want to be able to manipulate both electric and magnetic fields around your quantum dot. And you do this by adding all these metallic gates. You have wires that create magnetic fields around the qubit and so on. And then finally, you can put, for example, two quantum dots next to each other. And since the two quantum dots, if they're close enough, have exchange interactions between them, then again, you can create entangling gates. Okay. So again, hopefully this gives you somewhat an idea of what these quantum dots look like. So with this, I covered the two examples of quantum devices that I wanted to talk to you about. I'm not going to talk about defect centers because I think you'll probably hear about them in the next tutorial, but you will surely hear about them in the talks this week. Any questions about this first part? Yeah. We'll talk about that. We'll talk about that very soon. For example, the quantum dot, just to give you some numbers, superconducting qubits, the experiments that have been done so far are with up to 50, 70 qubits. Quantum dots, only a few. I think the largest experiment that I know of is probably 6 qubits. These are very challenging for a lot of reasons. Happy to talk more about it if you want later. We'll see. Actually, sorry, superconducting qubits IBM has recently built a chip with like 1,000 qubits. They haven't done any experiment on it yet, but they have it. They say they have it, so as long as you trust them, they have it. We have not seen any actual experiments on it, so we'll see how well it works. That's all I mean. Sorry, I do trust that they have it. So let's switch now to the quantum. Yeah, sorry.
You highlight some of the challenges in the system as well, so the limitations.
Yeah, so towards the end, I will sort of summarize limitations for kind of all of them. Each of these has kind of different pros and cons. I think what is nice about the engineered quantum devices is that they're on a solid system. So it's basically a chip, which is what we're, in a sense, more familiar with computers in general. Two challenges that both of them have is that they both need to be in a fridge. They both need to be at very low temperatures, which makes things quite complicated. If you look back at the picture of the superconducting qubit system, a lot of these cables that you see up here are for control lines for the superconducting qubit because you need all these microwaves. The scalability is pretty challenging. Again, we'll see how this 1,000 qubit device works. Maybe it's amazing and they figure something out to make it easier to scale, but that's pretty challenging. With the quantum dots, it's been very challenging so far, mainly because of materials problems, but recently they've started to do things with silicon more, and so it's a silicon-based device that they're using right now, and things have gone better. With the previous material, the coherence was terrible and they had a lot of problems. So I would say it's a bit too early to say if they will be able to scale to large numbers. So the scalability with the solid-state system is one of the biggest challenges. There are others, but it's a long list that maybe we don't have time to go through. But towards the end, I will sort of give you like an overview of the different challenges for kind of all of these platforms. Yeah.
Part of that overview, will you also talk about the sort of the noise landscape of these different
I won't go too much in the details because each of these systems has a very different noise landscape. But that is definitely a common challenge to all of these platforms. Of course, they have different sources of the coherence. So, for example, the quantum dots, well, in a sense, both of these, the control happens through these electric and magnetic fields. And so to be able to deliver this to the device in a controlled way, but without having spurious interactions with the outside, can be challenging. And so you need to do things very carefully such that, you sort of turn on the interaction with the outside only when you want to, but you turn it off when you want the system to be coherent and protected from the outside. That is one common, let's say, source of noise. Superconducting qubits has this very strange thing. They see basically, they have these macroscopic effects where they see noise due to cosmic radiations, and they haven't figured out exactly how to solve that. There are different things that people are trying to do. So there is a plethora of things, but they're very, platform dependent. So I won't go too much in the details of each of them because of that. But happy to talk about it later if you have specific questions. Any other question on this first part? Yeah.
I guess how is the software that's interfacing with the quantum dot so far?
How is the software? So it depends on a lot of things. So again, this is platform dependent, depending on how you control your system. But so each of these platforms have developed their own software control. Basically, what it looks like is you need to be able to interface with your classical controls. There are, currents. They are, for this other part, there are laser amplitudes and frequencies and things like that. And so you have all of this controlled on some classical computer that needs to interface with all these different things. Okay. And of course, there are different, depending on what are the timescales of the gates and things like that, what you need to use to interface with this is a different hardware, and then the software also needs to adapt to that. Okay, so let me switch to this other side, which is the side of quantum particles. And here we'll mainly talk to you about atoms and ions, because photons are a very different beast, and it will take too much to introduce that one as well. But let me start with trapped ions. So I start with this because this is one of the very first quantum computing platforms. The first ideas on how to use these for this purpose were put out by Sirac and Zoller in 1995. And I think here the idea is pretty simple. You have these quantum particles that have discrete energy levels, and so it seems fairly straightforward to isolate two of their energy levels to create a qubit. And also ions, have a charge, and so they can be trapped using electric fields. So if you think about it, it makes sense. We could create controllable qubits using the ions. As you see, it's a nice idea. It's not that trivial as it isn't with any other of the platforms. But the first thing that you need to do, again, as we saw with electrons in quantum dots, you need to trap them, right? You want to confine in space that ion so that you can then manipulate it and use it to store information. And so you would like to trap it in 3D. So ideally, what you would like to do is to have an electric field that confines the charge, the positive, let's say it's a positive ion, along all directions. But unfortunately, Gauss' law prevents you from doing this, right? You cannot have a divergence of zero in a point in space along all three directions. And so what people came up with is what is called the pole trap. So here you use time-dependent electric fields. And the idea is you create so here I'm only looking in 2 dimensions. You have a quadrupole potential that at any given time is trapping along one direction and anti-trapping along the other one. But if I switch between these 2 different configurations very fast, where the confining and the anti-confining directions switch, if I do the switch between these 2 very quickly, then the average trapping potential that the ion sees looks like this. So it's a harmonic potential along all directions. And then you add a confinement along the third, and so you get yourself a 3D trap. So this is a picture of an ion experiment where you can see the electrodes. So the ions would sit here in the middle. And what you get there in the middle of this trap is typically a 1D chain. So what people do is to have a strong confinement along 2 directions and only a shallow trap along the third one. And so along the shallow trap direction, you can have many, many ions, where the distance between the ions is determined by the fact that they have Coulomb repulsion. So they're all positive charges, so they repel each other, but you also have the confining potential, so the balance between the 2 gives you the spacing between the ions. Okay, so this is what you get in one of these pole traps. And then what you want to do once you have trapped the ions, you want to cool them down so that you have this nice controlled quantum system. And the way you do that is by using laser cooling. So basically the way this works is you have your ions and you kick it using photons. So you send photons from different directions, and the photons provide a momentum kick to the ion to slow it down. So when an ion is hot, it means that it's moving around very quickly. You keep punching it from different directions until it sort of stops. So you load the atoms in the trap, then you start doing laser cooling. You cool them down, ideally to the motional ground state of your trap. And then how do we encode the qubit here? As I said, this is fairly trivial for these quantum particles. You just want to isolate two electronic states of the ions. You can choose different solutions. These are the most common for trapped ions. You can either isolate two hyperfine states in your ground state manifold, or use an optical transition between your ground state and some metastable state. These are the typical implementations right now. And now if you want to perform single qubit operations, you simply drive transitions either in the microwave frequency regime or in the optical range using external electromagnetic fields. Which means basically you either send some microwaves just to the chamber in general, or you shine laser light onto your ions. So finally, how do we do entangling gates? This is a very nice thing about ions. So since they're all trapped into the same harmonic potential, they have shared motional modes. Basically, what you have in there is as if, in between the ions you had springs. So they're all attached to each other. If you kick one of them, they will all move together. And you can use the shared motional modes as a quantum bus to transfer quantum information between the ions. So since they're all connected, if I do something to one of the ions, I can then use the shared motional modes to map that information to another ion. And it doesn't need to be the ion nearby. It can be an ion at the other end of the chain. Okay, so this is how they use the Coulomb interaction to create entangling gates. Okay, so let me switch to neutral atoms. Neutral atoms are, in a sense, very similar to ions. They have very similar properties, but in other ways are kind of different. The particular implementation of neutral atom experiments that I will look at here are atom arrays. It's not the only one, but it's the one that is mostly used for quantum computing applications. So what you have here is an array of atoms. Again, similar to what you had for ions, but in this case is most commonly in 2D, let's say. So again, what you want to do here is to do laser cooling, same idea, kick the atom using photons. In this case, you want to do it before trapping. So let's say you have a gas with hot atoms. You start doing laser cooling, and then afterwards you trap. And for the trapping, in this case, the atoms are neutral, so you cannot use electric fields. In this case, we use optical dipole traps. So you use the laser light to create a dipole potential for your atoms. Again, here I'm not going into the details of how the interactions between light and the atom works, but just trust me, if you have a tightly focused laser beam, that represents an attractive potential for the atoms, and so you can use this so-called optical tweezer, which is simply this tightly focused beam here, to trap a single atoms. And so if you put a few tweezers next to each other, you can trap an array of atoms. Now, the nice thing about the way atoms are trapped is that you can create arbitrary arrangements with the atoms. Just moving the tweezers around, you have these lasers, you just arrange them in whatever geometry you want. And so, for example, here you see you can trap the atoms in a square lattice. This is a honeycomb lattice, a triangular, and so on. And our favorite demonstration of this arbitrary arrangement is we created during my postdoc a little video with the Super Mario jumping around, just to show you can really, what happened here. We were just moving the lasers around to move the atoms and create this nice little movie. So next ingredient that we need here is, since we have neutral atoms here, how do we make them interact? The atoms in this tweezer are a few microns away from each other, so there's no natural interaction. So we need to work a little bit harder to make them interact. And what we do is to excite them to a so-called Rydberg state, which simply means that you promote the valence electron to a high up orbital, such that the electron is now far away from the nucleus. And so you have a strong dipole moment in your atom because you have a negative charge that is separated from the nucleus. So you have a strong dipole moment, but also the nice thing is that you have a fairly long lifetime for these excited states, which is a few hundreds of microseconds, sorry. So it's long enough that you can do something within that lifetime. So now if you have two atoms in these Rydberg states, they both have a strong dipole, and so they interact with each other through dipole interactions. And so this is what we're gonna do to have interactions and then generate entanglement. So at this point, how do we do qubit encoding? This is very similar to ions. You just choose a pair of internal states that you use as your qubit states. And for quantum computing applications, you typically choose two non-interacting states, as for example, the hyperfine states of your ground state manifold. And then you only temporarily excite to the Rydberg state to mediate interaction. So your atom sits typically in these hyperfine states, so they don't interact. But then when you need to create an entangling gate, you bump them up to the Rydberg state, they interact, you have entanglement, you bring them down. Again, here, to do single qubit operations, you just drive transitions between these internal states using external electromagnetic fields. Again, they can be microwave, they can be lasers. And finally, how do we do entangling gates? So if you have two atoms sitting next to each other and you promote them to the Rydberg state, they will have van der Waals interactions between them. And so if you engineer the proper time evolution under this interaction Miltonian, you will generate entanglement between them. Okay, so with this, I hope I gave you some ideas of how people look at these different types of system, either engineered quantum devices or quantum particle, to store information and engineer logical operations between them. Questions? Yeah.
So does the noise increase when you get into the Rydberg state?
Yes. So the Rydberg state is more sensitive to a lot of different sources of noise. For example, since you have a dipole, if you have electric field noise, then you feel it. Whereas when the atoms are in the ground state, they don't really care if there is electric field noise. That's an example. Second, as I mentioned, there is a finite lifetime for these Rydberg states, so that matters. You cannot stay up there forever because at some point the electron will decay back to its ground state. And also there are some other details related to how you do the excitation. So to have the when you excite to this Rydberg state, the way you do the excitation can lead to decoherence effects. So yes, going to the Rydberg state makes things a bit more complicated, but you need it because otherwise there's no way to achieve entanglement. Yeah. So maybe here I can give you some numbers, since I give you some number for the quantum devices. So with atoms, people do experiments with hundreds of atoms pretty normally. I think the biggest is probably 400 atoms, as if I remember correctly. There are, similar to IBM, there are devices with a few thousand atoms. I think the biggest one has 6,000. Again, no actual quantum experiments done yet, so we need to see how well they work. For ions, it's a bit trickier because things work very well in 1D. They're way more complicated if you try to put them in 2D. So experiments with ions have been limited to a few tens of ions. Okay, but this should give you an idea of the scaling. Any other question on this part? Yeah.
So how big is the Rydberg orbit?
The Rydberg orbit, I think, is like 100 nanometers or something like that, depending on what state you choose and what's the atom. That's more or less the, yeah.
Multiple of these approaches include laser cooling. Do you have to account for a Doppler effect when you're doing a laser cooling, and so it's a statistical cooling, not necessarily at a particular wavelength?
So yes, that's correct. You need to take into account the Doppler shift when you do laser cooling, but the laser cooling techniques have this built in. So it takes into account that you have Doppler cooling, that you have Doppler shifts. The Doppler shifts are one of the reasons why you need the atoms and the ions to be cooled to the emotional ground state, because imagine you're shining your laser to excite some transition. If the atom is moving, then it sees a Doppler shift. And if the atoms have different frequencies, it means you cannot tune to that frequency. You will just have a disorder and so noise, and et cetera, et cetera. Yeah, that's a good point. OK, anything else on this part? OK, so just to sort of summarize here, if I had to say, like, over these different platforms, what has been achieved so far, it's actually a lot. There's a lot to be happy about. As I said, experiments have been done with tens to hundreds of qubits with good control on individual qubits. I said at the beginning, there is this rivalry, right, between controllability and scalability. But people have managed at least to deal with hundreds of qubits while maintaining good control at the individual qubit level. And these numbers are true for atoms, superconducting qubits, and ions. As I mentioned, quantum dots have much smaller numbers. Defect centers also have smaller numbers, but those have different applications as well, so it doesn't really matter. Another thing is, as I mentioned, the first platforms with a few thousand qubits have been developed, both for superconducting qubits and atoms. It still remains to be seen how well they work when you try to do something that is actually quantum and coherent. And finally, people have demonstrated gate fidelities both at the single and the multiple gate, multi-particle gate level that are compatible with quantum error correction, which I will talk about in a second. Meaning the gate fidelities are good enough, are pretty good. They could be better, but they're good enough for certain applications. And again, these have been achieved for basically all the platforms that I showed you. So what are the main challenges? As we said, we need to scale to millions of qubits. These thousands is great, but we need way more. And this is a challenge that I think we don't really know how to get to. There are some ideas to make each one of these platforms bigger, but nobody knows how to get to millions, I would say. Maybe some people do, but they keep it secret. One idea is to create multiple modules of these quantum platforms and then connect them using photons. And the next talk on networks will help you understand how that would work. So you keep the coherence between the different parts of the module, between the different modules, using photons that are also coherent and entangled with the different modules. Of course, we would like to improve gate fidelities even further. The higher the gate fidelities, the lower are the constraints on these quantum error correction architectures that I will tell you about in a second. Then we would like to develop more flexible architectures, because remember, we want these to be universal quantum computers, so we want them to be able to do everything. And so far, we can do some things. We cannot do everything. And finally, one thing that I would like to mention is, as we said before, you have these quantum systems, but of course, there are layers of classical controls that you need to interact with these quantum systems. And these need to be made more and more efficient if you really want to be able to scale to millions of qubits. OK, so here I would like to close the platform section and talk briefly about some applications. I just want to give you a flavor of what are the things that people have been able to do so far. And so I will only talk about two things. And again, you will see a lot of things in the next few days. So I'm not worried that you will not know enough. But one is quantum error correction. I would like to give you an idea of why we need millions of qubits. What are we trying to do when we're trying to build this universal quantum computer? And then the second aspect is that of quantum simulation. As I said, this is probably the field where we've made the most interesting discoveries and have achieved the biggest results so far. OK, so let me start with error correction. So I assume not many of you know what quantum error correction is about. So let me briefly tell you what that is. Even in classical computers, you have a certain chance that an error happens in your circuit. So how do you deal with this? In classical computers, you just make copies. Instead of having a single bit, you create 3, for example. And so you have some redundancy. So let's say an error happens on one of these, and it flips to a 1. When you look at the bits, you're like, oh, there's a 1 and 2 zeros. The 1 is wrong, OK? And you keep the 0. What is the problem when you do quantum error correction? There are some conceptual challenges. the same reasons why quantum mechanics is cool is also there are also the reasons why it's hard to deal with. So first of all, there is a no-cloning theorem. So no way of making copies. You cannot do that. But even if you assume that you can make copies, you cannot just look at your 3 qubits and say, oh, let's measure them. One is 1. I'm gonna, kick it out and just keep the 2, because every time you measure, you collapse the system. So you need to find a way of checking for error without collapsing the state of your system. And so how do you do quantum error correction? You need to introduce some redundancy, but in a different way. And so the idea is to use entanglement to store information non-locally on a larger system. So instead of using a single physical qubit, you take many qubits and you encode your information in this entire array instead of just in 1 qubit. And the array needs to be entangled so that all the atoms sort of share in some way that information. And if your information is delocalized, that helps you to be protected from accidental errors. So let's say that one of these qubits flips because of some interaction with the environment. It doesn't matter because the logical qubit is only slightly affected by that, and so it won't break the information completely. And the way you can detect the errors is by measuring stabilizers. So instead of measuring the state of a single qubit, which would make your qubit collapse, you measure what are called stabilizers. So the stabilizers are basically products of operators. So instead of measuring, let's say, the X operator on this qubit, you measure the products of X's on this square. And in that way, you don't project. You are able to detect errors without perturbing the information. Okay, so I'll just give you a quick example. If you stay in the field of quantum computing in any ways, the toric code will come out of your eyes at some point. It's one of the most famous error correcting codes. So let me just give you a quick overview of what it looks like. So again, you have this array of qubits, and you have each of these dots here is a physical qubit, but your information is stored in the entire array. So this is your logical qubit. Instead of storing information in 1 qubit, you have many qubits in your array. And the stabilizers, as I said before, are products of single particle operators, for example, and you have 2 types in this case. You have the Z check and the X check, because you want to detect both types of errors that we were talking about before. You want to be able to detect bit flips, but also phase errors. And so you have these 2, and they look like this. So the X check is the product of X operators on the square, and the Z check is the product of Z operators on the cross. So the error-free state is the one where all the X and Z checks are equals to 1, to +1. So what happens when there is, and you detect the state of the logical qubit by measuring these strings of operators, but that doesn't matter too much. When there is a physical qubit error, let's say that the qubit here flips from 0 to 1 or vice versa. What will happen is that when you measure the stabilizers around this physical qubit, you will see that they flip to -1 instead of being +1. So you measure and you're like, oh, an error happened. You can identify it, and you can also, in principle, correct it. Okay. So why do we need this big logical qubit? When you increase the size of these logical qubits, so the so-called lattice size, on one side, you have more opportunities for errors, right? You have more physical qubits, so you have more places where an error can occur. But at the same time, you have more redundancy. So there is a threshold behavior. If your error rate is low enough, it's the same thing actually with the classical error correction. If you have too much probability of having an error and 2 of those flip, then you would interpret your bit in the wrong way because you have 2 ones and you're like, oh, it's 1. Wrong, it's 0. So there is a threshold behavior. Your probability of having an error needs to be low enough that you don't interpret the wrong thing. And so this means that, for example, for the toric code, you need that the probability of having an error is smaller than 1%, which of all error correcting architecture is one of the highest. So it's not that bad. People have achieved this in different platforms. I want to mention this error correction idea because it was really the fact that people understood how to do error correction that really allowed the field of quantum computing to take off. Before people realized how to do error correction, it was thought that quantum computing was actually impossible because it seemed like errors had too much of an impact on this kind of applications. And it is well understood that we need to be able to do error correction and use logical qubit to use these quantum computers. There's no way of encoding information just in the single physical qubits. So I would like to show you where people are at in terms of developing quantum error correction. So until just actually a few months ago, the demonstrations on quantum error corrections were limited to 1 or 2 logical qubits and 1 or 2 logical gates. So again, now you have this, you have that your logical qubit is encoding in an array, and now you need to also do gates between the arrays, right? So both of those things you need to demonstrate. This is, for example, an experiment from Google from about a year ago, actually probably less. And these were demonstrated using superconducting qubits and trapped ions, but again, the size of the circuits were fairly limited. A really big breakthrough happened recently using atom arrays. And you will see this probably in Misha Lukin's talk, I think tomorrow. In this experiment, we've done operations using up to 40 logical qubits. So imagine each of these logical qubits is made of several physical qubits. And then up to 20 logical CNOT gates, which is one type of entangling gate. So with atoms, things are moving really fast, and the scale of these logical operations is increasing pretty impressively, I have to say. But I think there is a lot of room for improvement also with these other systems. The thing is, with atoms, the scalability is a bit easier. So it's much easier to have, up to like a few hundred atoms using a few hundred qubits using atoms than it is with those other platforms. Okay. So I hope this gives you an idea, since quantum error correction is necessary, at least as far as we know now, there could be some breakthrough that makes quantum error correction unnecessary, but so far it's pretty, it seems to be pretty necessary to the development of quantum computers. You can see where we are at in the development of these universal quantum computers. Some big things have been done with atom arrays, some small demonstrations have been done with other systems, but of course we need to do more to get to the ultimate goal. And then I want to show you one quick example about quantum simulation. I just want to show you one experiment that I did during my postdoc that kind of shows you that we've done things that really we wouldn't have been able to study using classical computers. So that's already a frontier of quantum platforms where you can see that there is already quite a big advantage compared to classical computers. And so the example that I want to show you is related to topological quantum materials that, again, have a lot of interesting technological applications. So in the 70s, Philip Anderson postulated the existence of this so-called quantum spin liquid, which is a material that is supposed to have several interesting features. The first one is it has long-range entanglement, meaning you have this piece of material where the electrons on one side are entangled with the electrons on the other side, even if it's a bulk material with a lot of stuff in it. And also it has topological properties. Topological properties are things that are related to the shape and the geometry of an object. So the famous example is that in a topological sense, a mug is the same thing as a donut because you can smoothly deform the donut into a mug and vice versa. Basically, the characteristic is having a hole, whereas something like a ball is a different topological object. You can only change the topological property by breaking the donut and then gluing it back in a different shape and so on. So why are these topological properties interesting? You can use this for quantum computing applications, actually. And I think you will have a talk about topological quantum computing at some point. So I won't go too much into it, you'll see it. But basically, I showed you that you know, to have robustness to errors, you would like to store your information in some bigger system, like the array that I showed you before. If you have a topological system, you know, this robustness to errors is even better, because let's say you have the donut and you encode your quantum information in the topological properties of that object. So it's either being a donut or being a ball. Let's put it like this. If you just remove a crumble from your donut, which corresponds to a single qubit error, it's still a donut. It doesn't change. It's not going to become a ball because you remove a crumble. And so it's inherently robust to this type of errors. And so the idea is that if you can create this type of topological states, then you have inherently a way to be protected from errors that actually doesn't need error correction in principle. Okay, so since the 70s, people have been trying to find this spin liquid in many different condensed matter systems. There have been some hints to it, but no very conclusive observation yet. What we did in 2021 was to realize this topological spin liquid using these atom arrays. Basically, you can tune the interaction, the Miltonian of our atom array, such that, you know, the ground state phase of your system is indeed that quantum spin liquid up there. And so that's what we did. And again, I won't go into the details because I really don't have time. But this gave us unprecedented insights into this topological matter. This is a great example of quantum simulation. We did something in the lab that we would like to be helpful for the development of a material. Not happened yet. Hopefully, it will at some point. But at least it allowed us to understand better how this spin liquid phase works. And it's, again, a new tool that is kind of complementary to what analytical theories and numerics can do on these types of topics. There are some connections to nuclear physics problems that exist between these topological systems and some nuclear physics phenomenon. We gained some insights for the design of topological materials. We know what are the kinds of interactions that created this material for us. And so potentially we could help look at actual materials that have similar properties. And also, again, as I said, this is also related to a potential new way of doing quantum information processing. Okay, so with this, I just want to conclude. So we started saying, you know, what is actually happening. So let me just briefly summarize at least what is my point of view. So I think it's a new, exciting interdisciplinary field that combines basic science, device engineering, applications, and eventual products. As Nishan pointed out at the end, you know, this is a field that now really needs the interaction between all these different fields to move forward. And I think it's really exciting, at least for me, being involved in this field. It means that you really need to be able to talk to people from very different backgrounds to really move forward. We are in this era that I called of quantum discovery because we're using these machines for scientific applications, as I showed you with this last example on the topological materials, but we're also on the cusp of quantum industry. I mean, there is potential for real-world applications and products that is not there yet, but seems closer and closer every day. You know, still fairly far, I would say, but you know, we're doing big steps in the right directions. So with this, I would like to thank you, and I'm happy to take any more questions. Yeah. Yeah, kind of. Let me see how I can say it. This topological phase is related to, can be mapped on specific lattice gauge theories. And so basically, studying this type of topological states, you can also get some insights on what are the expectations for those lattice gauge theories. And actually, there is a whole new field that is developing now on different types of lattice gauge theories that you should be able to simulate using these atom arrays, because the type of interactions that you have here map onto some lattice gauge theories. They're still, in a sense, like toy models. I wouldn't say that they simulate anything that is super relevant for any actual nuclear physics system. But what the theorists tell me is that even just understanding the basic ingredients of these lattice gauge theories would be helpful for them to be able to develop the next step. So this is definitely a direction that quantum simulation, at least with these atom arrays, is taking on since the past couple of years, I would say. Yeah, thank you. Yeah?
Earlier it was mentioned that there's a big push for the universal architecture for quantum computing. But why is that wanted, given that in classical computing, we have all of these different architectures like GPUs, CPUs, each with dedicated purposes? Wouldn't it be more effective to have
That's a good point. I mean, yes, no, that's definitely a good point. I think when you mean universal quantum computer, in a sense, it's what the classical computers does now, which can host all these different, GPU, CPU, and so on. I think yes, in a sense, it's something that can put together all these different architectures. Right now, we're not anywhere near having something like that, Yes, so I think you have a good point, and I think there are people that also believe that maybe some of these platforms will always be better at some specific things, and others will be better at other specific applications. And so maybe the future is just using these different things for different specific applications. Maybe we will never get to something that is completely universal. But I think what I mean by that is, still with the CPU, you can do a lot of things. Right? We're nowhere close to that. We're very far. When I talk about this programmable quantum simulators, you have devices. For example, this atom array here can do specific Hamiltonians, and so can simulate specific type of phenomena. But it's still fairly narrow, right? So you cannot do a lot of different things on that same machine. We would like to get to a stage where, the range of applications for a single device is a bit broader. Does that make sense? Yeah.
You started and ended this talk talking about how it's like an interdisciplinary field. So my question is, how much of this it's a field in which people from different expertise can come together and work together and push this field forward, versus there needs to be individuals who are themselves multidisciplinary and have their kind of like fingers in a lot of different pies inside to be able to apply and push this field forward?
That's a very good question. I think, at this level, it's really impossible that a single individual can master all of these things at the same time. I think personally, being an experimentalist in this field, I do try to, as much as possible, at least, gain some understanding on the different pieces that are involved in this, but there's no way that I'm going to be an expert on all of them at the same time. And so, for example, what we're trying to do here at Harvard, and I think is very common in a lot of universities now, is really try to put together as much as possible all these different backgrounds such that you have collaborations between different people. And honestly, for each one involved is amazing because you learn a lot, but at the same time, you can keep being an expert on one of these aspects while working together with other people that bring in, their different skills and knowledge to complete the picture. I mean, it is true in a way, there's also a lot of thoughts about what is the education that we need to provide to someone who wants to do quantum science. And I think in that way, we're trying to make it a bit more multidisciplinary, but again, we're still limited people that cannot, know every single thing at the same time. So, there is an attempt to make the education also be more varied, but that being said, I think, there is so much that needs to go into it. And one aspect of this, I think, when I talk about the applications, I think there is probably so much more to explore. And to be able to know what we can do with these quantum computers, it means that we go out there and we talk to people and say, hey, this is the machine I'm building. What do you think you can use it for? Because some of these people have no idea what this means. And so you need to tell them, these are the capabilities. Can I help you with something? So I think it's really a nice thing about quantum science at this moment that really needs to bring together different people in order to actually grow into what it promises to be. Yeah.
Expertise that you're bringing to the field, that there is a specific niche that you're going to find yourself working within, or is it really that all these fields are so interwoven anything that your expertise can pretty much be found and utilize anywhere?
I mean, I think it depends. So I think you will see in this conference in these days, you know, when we talk about quantum science, there are many different things that we're talking about. Today, I talked mostly about computing and simulation, but you will hear in a second about networking, you know, there's sensing. And I think in all of this, I can see, you know, you need physicists and you need, in a way, like some engineering level. Depending on the platform, it might be electrical engineering. There is a lot of software engineering that needs to go into it. So I think it depends a little bit on the application, but there are some common skill sets that are useful to basically all of them. I think physics is certainly like a predominant one. But again, there are different levels of engineering that really need to go into this. I think what kind of engineering kind of depends on the application a little bit. But for example, software engineering is everywhere. You know, then there is the chemistry part that is common to a few of these applications, maybe not all of them. I think it depends a little bit on the skill set, but you know, many of these applications require a lot of them, so there is a good overlap in the different.
Yeah, one of the things you should consider, though, is that as you embark on a scientific career, your scientific career is going to be a random walk through science, right? It's going to change depending on how your interest changes and things you learn and how science evolves overall. And so none of us stays in these boxes.
Yeah, that's true. Yeah, I'm a physicist, but now I'm in the engineering school, you know. And again, I'm in applied physics. I'm shifting a little bit towards something different, and I didn't know at the beginning that I would find myself there. But yeah, I see many people that have done even more drastic changes during their career. Mine is kind of a slight shift. There have been bigger shifts that I've seen in other people, but yeah, that's very much true.